Chapter 7 is on exponential functions, which is kind of perfect for right now that we're living through the COVID-19, the coronavirus. The coronavirus, if you've been paying attention to the news, the newscasters will say that the number of people infected with the coronavirus is expanding exponentially, and the kind of functions that we do in this chapter, they could be used to predict how many people will have the coronavirus at some point in the future. In fact, all the models that mathematicians are making to predict, how the horrible disease is going to spread through our country involve exponential functions. And when we get into 7.3, the last section in this chapter, I'll try to make a problem up that is more relevant than these are. Real generically, an exponential function is just a function where the x is in the exponent as opposed to a base. In section 7.1, each problem doesn't have really anything but a function written with function notation that's an exponential function because there's an x in the exponent. We're going to do a real limited number of these problems, and this is the homework that you're going to be asked to do for section 7.1. So what's that? 1, 2, 3, 4. It's 8 problems. And each of the problems in this section, we're supposed to do a few things. First, we're going to plot 5 points. We're going to sketch a graph. We're going to find the domain and the range of the function. So I'm going to make a table and plot 5 points. It doesn't actually say make a table, but I'm going to need to. I'm going to make a table that has 5 points. After I get my table created, either doing it by hand in my head, using the table feature on my calculator, or finding each line of the table individually on my calculator, I'm going to make a table. I'm going to plot the points. I'm going to sketch a graph. And then I'm going to find the domain of the graph, which is the left edge and the right edge if the graph is unbroken. So I'm going to find the domain. And for exponential functions, because the graphs will turn out to not have any breaks in them, the domain, when we go to do it, we're just going to describe the left edge and the right edge of the graph. So plot 5 points, make a table with 5 points in it, sketch a graph. Once you have the graph, state what the domain of the graph is and state what the range of the graph is. These are unbroken graphs. The domain is going to be from the left edge to the right edge of the graph, and the range is going to be from the bottom to the top of the graph. I can explain everything without actually breaking out my calculator to finish up a table and sketch a graph with quicker than I can to do an entire problem. So instead of doing all the problems one at a time, I'm going to globally just talk about the theory that we're going to apply, how I'm going to decide on what the appropriate table for a graph is going to be, how I'm going to know what the domain and range are of the graphs, and then I'll get into the messy details. So I put little brackets around the problems that I want you to do, and then I just underlined some problems that I'm going to do because I figured 1 and 2 are similar. If I look at 5 and 6, they're similar. 10 and 11, they're similar. So I'm going to do problems that are similar to your problems. And before I do individual problems, I want to talk about the theory that's necessary to get through this section to make it easy. So for the problems that I'm going to do, problems 2, 6, 10, 22, 28, 32, and 34, I'm asked to make a table that has 5 values in the x column, sketch a graph, find the domain, and find the range. It's super easy to do all of this without a calculator in terms of get the table started, know what the domain, and know what the range of the graph is. If the exponent is just a naked x, like in problem 2, the exponent doesn't have a plus or minus after the x. If the exponent is just a naked x, like it is in problem 2, and like it is in problem 28. In problem 28, the plus 3 is not part of the exponent. It's kind of a base in some sense. In problems 6 and 10, the number that's next to the x is part of the exponent. So if the exponent is just a plain ordinary x, in my x column for my table, I'm going to put -2, -1, 0, 1, and 2. So in problem 2, because the exponent is just a naked x, I would get that for my starting table for my x's. And in problem 28, the exponent is just a naked x. So if I'm just trying to put 5 values in my x column, those 5 values would be -2 to 2. For the rest of the problems that I haven't touched yet, the way I'm going to get my x column of my table started is I'm just going to look to the exponent and I'm going to change the sign of the number. I'm going to put that in the middle of my x column. So when I eventually go to graph problem 6, the exponent is x minus 2. I'm going to change the sign of that -2 to +2 and then go smaller and then bigger. The table that I would use to graph number 6 and the x's would have 0, 1, 2, 3, and 4. If I was doing a table for problem 10, because the exponent isn't just a naked x, it has an addition or a subtraction sign. That one has an addition sign. If the exponent has x plus a number, you just take that number, you change its sign, put it in the middle of your x column, and then go smaller and bigger too. Smaller than -2 is -3 and -4. Bigger than -2 is -1 and 0. The exponent on problem 22 is x minus 1. Again, if I'm going to make a table for this, because the exponent has a subtraction in it, I'm just going to change the sign of that -1 to +1. Go smaller, put that in the middle of my x column. Go smaller and then bigger. And those are the values I'd used. And then I'd get my y's either by hand without a calculator, one line at a time using my calculator, or using the table feature on my calculator. For problem 32, the exponent is x plus 2, the exact same exponent as problem 10. So I'm going to get the exact same table. The +1 that isn't in the exponent, that makes kind of 10 and 32 different, doesn't impact my starting table. My starting table is 100% based on the exponent, and the exponent in 32 is x plus 2. I'd put a -2 in the middle of my table, and then smaller is -3 and -4, bigger is -1 and 0. And then the last graph that I'll do in this section, the exponent is x minus 3. These numbers that aren't part of the exponents, they wind up impacting the range, but not the starting table. In problem 34, if I was going to make my starting table, in the middle of my x column, I'd change the sign of the x minus 3. The -3 will go to +3, and then I'll go smaller and bigger. That I can do without a calculator. I should know what my table can be. And it turns out that even without having a graph, I can explain to you what the domain and the range are. The domain I can do kind of theoretically what it is. The range, without having a graph in front of you, the range is really a calculus question. I can't really explain the calculus, but I can tell you how to find the range, and then when we get to the graphing, I'll show you how the graph works. So for these exponential functions, every domain, so the domain for each function we graphed today, for each function in section 7.1, is going to be all real numbers or -infinity to infinity. because there aren't any numbers I can plug in and have bad things happen. When we graphed square roots, there were numbers that I could plug in and get i's out, and those didn't show up on a graph. And earlier in the semester, when we found the domains of fractions, there were numbers I can plug in for x and get undefined. But for exponential functions, there aren't any numbers that I can't plug in. If I looked at problem 2, just to try to explain this, the reason the domain of every graph that we do today is going to be all real numbers is because no matter what number I plug in, like if I plug a number like 4 in, I can't get an I and I can't get an undefined. If I plug 4 in, I'd get 2 to the 4th power. That's not an I, that's not undefined. That number is going to be part of the domain. If I plug a negative number in, I'm going to get a fraction, because negative exponents you can make positive by creating fractions with ones in the numerators. If I plug decimals in, that's like doing an ugly radical. That I can't do without my calculator. If I plug a decimal in, I just randomly picked up a number. But I'm not going to get undefined. So, or I'm not going to get an I, because there's no number that I can plug into any of the exponential functions that we do today that would give me undefined or an I. There aren't any numbers that I can't plug into the function, which means the graph is going to be unbroken from the left edge of the x-axis to the right edge of the x-axis. The domain of every single graph that we're going to do today is going to be negative infinity to positive infinity. So without even knowing what the graphs look like just yet, for every single graph, the part that asks me to find the domain, even though I haven't even showed you what the graphs look like yet, the domain of every graph that we're going to do today is going to be negative to positive infinity, because the graphs are going to be unbroken. They're going to go from the left edge of the x-axis to the far right edge of the x-axis unbroken. So for each of the 7 or 8 problems that I'm about to do, I know what the starting values for my x column are. I need to use probably some technology to get the y values. And I know what each of the domains are. No matter which graph I do today, every single graph in section 7.1, the domain is going to be negative to positive infinity, specifically because there aren't any numbers I can plug in to get undefined, nor i's, which will translate to the graphs being unbroken from the far left edge to the far right edge of the x-axis. The range isn't something I could explain so well without having a graph in front of me, but I can show you how to find the range real quickly. And then as we do the graphs, I'll try to show you graphically what the range is. So I'll explain what the answer to the range is, and then as we do the graphs, I'll show you visually how that range shows up, how we can identify the bottom and the top of the graph. And the numbers that I haven't highlighted yet in problem 28, 32, and 34, those numbers will actually be the bottom of the graph. So for domain, I read from the left edge to the right edge of the graph. For range, I read from the bottom of the graph to the top of the graph. The bottom 3 problems on this set of 8 problems that I'm going to do today, or 7 problems I'm going to do today, are going to have bottoms at the numbers for 28 at 3, for 32 at 1, for 34 at -2. And the bottom of the graph will be a part where the graph doesn't touch, where it stays microscopically above. The range for every graph that we do today is going to be some number, comma, infinity. Infinities always get round brackets for domains and ranges because you can't actually infinity is just a concept. If you square bracketed it, you would say that there's an absolute biggest number, but there isn't, because you could always add 1 to any number. The start of my range is also going to have a round bracket, because the graph isn't actually going to have to touch the y value that has that number. And each of the problems at the bottom of the sheet where there's a number that's not in the exponent, that's written after the exponent, that number is going to show up in my range. In problem 28, this plus 3 that's not in the exponent is going to be the start of my range, and infinity is going to be the end of my range. In problem 32, the plus 1 that's after the exponent, not part of the exponent, is going to be the start of my range. The end of my range is going to be infinity. And in problem 34, the minus 2 that's not in the exponent but after the function is going to be the start of my range. The end of my range is going to be infinity. For the rest of the problems on this sheet, there isn't a number added or subtracted that's not part of the exponent. And for each of those problems, 2, 6, 10, and 22, there wasn't a number that's not in the exponent, that's not part of the exponent. For each one of these, the range is going to be 0 to infinity. And when I get into graphing on part 2 of this video, I'll show you how the range shows up and how I depict it on my graph. So I should, for each of the problems that we're going to do in section 7.1, I should, just by looking at the function, know the values that go in the x column of my table. I should know what the domain is. I should know what the range is. Then I'm going to use either some sort of technology or by hand to get the y part of my table. I'm going to plot the points. I'm going to sketch a graph to finish up each of the problems. So I'm going to break this into a part 2 right now, and do a couple tables completely by hand, and then progressively get lazier. I prefer it if you just use your calculator table feature to get y's, but if you want to do y's by hand, that's fine as well. All right, so I'm going to pause and do part 2.